Yeah, so good morning, everyone. It's a huge pleasure for me to be here on stage and to talk about our NXP Automotive view of the world and what makes me tick. The unfortunate thing was I just showed you our RinSpeed video, so a video that we are doing together with the company RinSpeed since a few years. RinSpeed is a Swiss think tank, and they are doing since 40 years always a concept car for the Geneva Auto Saloon. Amongst others, in 2007, they did this swimming and diving James Bond car, the Lotus Elise. And as said, the unfortunate thing was that I'm only the techie here, the nerd, who has to explain the technological stuff, but I was not allowed to be the actor next to that beautiful lady in Barcelona in that video. But of course, let me use the next 40 minutes to tell you and then hopefully to explain with the right passion why I think that I have one of the coolest jobs in the semiconductor industry at the moment. And parts of that are, of course, linked to the fact, as Chuck said, that NXP and Freescale merged last year. So we announced that in March last year, took 9 months, and the wedding day was then December 7. So basically, ever since then, we are the biggest automotive semiconductor supplier in the market. So in the range of 14.5% market share according to Strategy Analytics, so quite sizable. We have 30 sites, we have 2,500 automotive R&D engineers, and about 40% of the NXP revenue are coming out of the automotive market. So for us, a quite important business. Next to the automotive business, what is important for you to understand is that NXP is the world's biggest crypto chip supplier. So basically for all sorts of banking cards, transport cards, but also passports. Most of the crypto chips are coming from us. And if you have your wallet in the pocket, for sure you're sitting on an NXP product. Yeah? But that's, of course, important for data security for the IoT. So what are the big trends that are fueling the automotive industry? Well, I think it's the three big that most of you know. So to the left here on the slide, it is basically the trend, of course, to being connected to the outside world. You wanna have connectivity in your driver workplace like you have it on your sofa at home, want to talk to the people, want to listen to music of your choice. To the right here on that slide, of course, it is the energy efficiency of the cars. So everyone wants to have a car that is rather consuming carbon dioxide than producing carbon dioxide, especially important for Volkswagen, but also a few others in the ecosystem. The most important trend for me as a techie is the one in the middle. And this is the trend to self-driving cars. It basically means that since 150 years, we see real big disruptions in the industry at the moment. And this is, of course, on the one side, the car is getting connected. So it's just a very, very expensive thing in the Internet of Things. That's one part. But on the other side, what we are seeing is we are converting now horse carriages that by accident have a combustion engine into robots that by accident have wheels. And that is literally, as I mean it, the two big trends that we see in the industry. And why is it so interesting for me? Well, look at the subtitle there. At the moment, on the roads of this planet, every year 1.3 million persons are dying. If I can only make a little contribution to saving a couple of lives, that would be for me, in my techie life, enough of a reward. And what do I need to do for that? Well, very simple answer. I need to get the human factor out of that equation. You see it here on the slide. 94% of all these fatal accidents and 50 million severe accidents per year are mainly caused by human beings. It's not surprising. So the other part would be material breakdown or flat tires or God knows what. But in principle, of course, the steering center of the car has malfunctions. And this is either a recognition error, so as a human being, that means I'm driving into the bright sunlight, I cannot see that the person is on the road, I hit that person. Decision errors, I go straight while I should drive around the curve or whatsoever. But more increasingly over the last years, also performance errors. So this is basically, I'm tired, I'm drunk, my performance of my compute system is not up to speed, but also texting and emails. When you are texting and when you are emailing, the likelihood of a severe accident goes up by a factor of 40. Just imagine that. And what we're seeing is we had a decline over the last 25 years in the road fatality rates in Europe and in the US. In the last 2 years, that is notching up again, simply due to the factor that you are not paying attention to what is happening on the road. And for that, of course, automated systems would do the job. They are never drunk, never tired. They don't care for the nagging kids in the back seat. They don't get emotional in a nasty traffic jam and whatsoever. So the whole industry is looking at what should we do? And basically there is two big trends. The traditional car makers are coming from that horse carriage side, I have to say here, over these various levels of automation that you see on the screen. And they are coming from level 1, getting a bit more assistance systems in, and just another assistance system and a better one, so that you basically can, at one point in time, take off the feet. You have automatic acceleration and braking, take off the hands, you stay still responsible. And then, of course, level 4 is take off the brain and the senses of the driver as well. Other companies who are not having a footprint in the automotive industry, for example, Google, they look differently at that picture and say, forget level 1 to 3. We are going from the robotics side directly into that whole game. Okay, what do we need to making such a self-driving robot reality? And basically what this means is it means replacing the sensors of a driver with electronics, so adding redundant sensor systems, which is radar, vision, laser scanners, so LiDAR as it is called here, ultrasound, and also communication outside of the line of sight. So in German words, you would say, in human words, you would say telepathics. So really getting information of stuff that is around the next corner, that is a mile ahead or whatsoever. And then, of course, what you also have is sensor fusion. You need to calculate a driving advice out of all of that. So just a very nerdy, techie picture. How is every robot built? Well, very simple. You have 3 compartments. A sensing compartment. You are trying to sense what's going around in the next environment. Then you have to calculate a driving advice out of that, so think. And you have to act, so basically sending commands to your arms and legs of the car. Very simple. The orange boxes, and that is the good news for us, the orange rimmed boxes here are the boxes where NXP has a market leadership position. So in other words, if you're looking at that, and also what we have in the infotainment part, so out of the Philips car radio domain, of course, we developed in the past a very nice portfolio on that. Also there, we have a very broad portfolio, and I dare to say that NXP is one of the very few, if not the only company that has all semiconductor ingredients for self-driving robots. And this, of course, makes us at the moment a bit the it girl of the automotive self-driving industry, at least from a semiconductor perspective. But of course, there's a lot of other semiconductor players in that market as well. And why the heck should NXP be so firmly entrenched in that market? Well, because there is other factors, and you see them here on that diagram, that I have called the robustness tetrahedron. It is not only getting consumer components into the market and then hope that the system sort of works and then you can reboot at every point in time and then do all of that stuff. No, it is basically managing 4 axes of this picture here, and which is, of course, getting the human factor out. I already talked about that, increasing the road safety by assistance systems. The automotive industry has worked since 40 years on device reliability. If you have 100,000 components in your car, you cannot afford every half an hour a breakdown of one of those components, because then you would never start driving. So the device reliability needs to be at its utmost level. But the main blocking factors for self-driving cars are the 2 others: functional safety and functional security. Functional safety has also arrived very well in the automotive industry, which is basically, we call it the ISO 26262 standard. It is making sure that the overall system cannot cause fatalities. So you're looking at a car, you're looking at what happens if the power steering fails, and then you classify this, and basically you try to make these systems fail tolerant, fail robust. So I give you an example. Failing of power steering, is that a fatal thing or is that a dangerous thing, yes or no? Well, the answer is it depends. In a Fiat 500, for sure, it is not a dangerous thing. In a Ford F350, for a 45 kilo lady, that might be a total different picture. Yeah? So it is really the system considerations that you need to take into account, and you work yourself down to the component level. And the same I called here functional security, which is basically not the component robustness, the system robustness, but the hacking proofness of such a system. And you all have witnessed in the press in the last year the GPEC, for example, where Andy Greenberg and some ex-NSA hackers could prove that they can remote control the car in a way you as a driver definitely don't want to have this. This is also an economic factor, mastering that robustness tetrahedron. And last year was not only the all-time high year in terms of car sales, it was also the all-time high in terms of recalls of cars. So, of course, for car makers, for the tier ones, for public, this is a huge economic factor. And of course, also there, we try to be a good supplier to this industry by making sure that we avoid these hazardous recall mechanisms and incidents over time. So what I want to do now is I want to talk you through a couple of examples and show you where we are, what is the disruptive stuff that we have in our kitchen, and how we're gonna try to change the auto industry. The first one is radar sensing. The next one is car or vehicle to infrastructure communication. Then about sensor fusion, Ethernet networking in cars, and data security. So I talked already about the need for sensing systems for autonomous cars, and basically radar is one of the systems of choice. So what we see is at the moment upper middle class cars have adaptive cruise control systems in the inbuilt, so a front-looking radar, 250, 300 meters looking ahead. This will be enhanced over the next years with a complete radar cocoon. So basically, it is a radar surround view of the car in all directions, 200-300 meters ahead, but also 150 meters to the back and 100 meters to the side. So basically that while you are driving or while you are parking, you have basically a complete surround view of radar. And this will increase the amount of silicon in cars significantly. 77 to 81 gigahertz are the the radar frequency of choice here. Why? Well, I have here such a tiny little radar sample in my hands, and of course the higher your frequency, the smaller your antennas. And these postage stamp size radar systems are only possible, of course, in the higher frequency domains. If you have 24 gigahertz or so, it's quite a sizable brick, that system. But you want to, of course, integrate these tiny systems around your car. You want to hide them away. You want to paint them over. And of course, the great idea that we had is, how would it be if we could have a standard CMOS radar front end? I had that dream with a few of our engineers in 2012, and a lot of people laughed at me and said, Lars, it's a dream on, but frequency-wise, you can forget this. 80 gig in a CMOS technology, it will not work, at least not with the power output that you need for 300 meters of radar. So I still remember I got a phone call Christmas Eve lunchtime 2013. Lars, we have taped out. The thing is in the factories. And yeah, in the meantime, we have it back, and you see this in the middle. The trend is, of course, we have a radar front end already in our hands, and now with the Freescale microcontrollers, we can merge this thing into a radar one chip. So CMOS front end, CMOS microcontroller, radar one chip going forward. And what we see is we see two flavors of radar systems coming up. One is these radar stems glued around your car, and the other thing is taking 4 or more of these front ends, putting a big fat microcontroller behind that, and let them run coherently. And this is basically a system with 3 send, 4 receive channels. So you can really have beamforming by antenna clusters, which is of course pretty nice because you get I call it high brightness radar for your cars. Yeah? In other words, we have now in the meantime a very interesting radar offering in our hands. And what you see here is basically the picture of this little radar stamp that I have in my hands here. It's of course a nice combination just to illustrate how NXP Freescale is going together now. The NXP transceiver, the Freescale microcontroller, the Freescale power management ICs on the backside, and the former NXP in-vehicle networking, so CAN and Ethernet connectivity. And in our laboratories, we are playing even with power over Ethernet, so we can supply this entire little thing here just via the unshielded twisted pair cable of the Ethernet, which saves, of course, quite a bit of weight in the wiring harness as well. Yeah? So coming now to a totally different thing is this famous vehicle-to-vehicle and vehicle-to-infrastructure communication, which is basically, you see it here, an IEEE 802.11 derivative. For the ones who don't know that, 802.11 is another word for Wi-Fi. So this is the standard Wi-Fi family as your Wi-Fi routers at home use it, as your mobile phone uses it. And the 802.11p is just a standard with higher output power, ranging over, in the open field, we have measured it over 1.5 miles of distance, and working to transmit messages up to 500 kilometers an hour of relative speed. Why the hell 500 kilometers of relative speed? Well, typical German use case, a motorway without any speed limit. One Audi A8 and another Audi A8 approaching each other at maximum speed is 260 and 260 kilometers an hour, so 520 relative speed. I don't know how often that is used in real life, but at least theoretically it's possible, and then it's also a lot of fun. The use case for all of that is, of course, what you want to do is you want to have hazard warnings. So motorcycle is approaching me and I'm just coming out behind a 40-ton truck or whatsoever, so it's very much appreciated by the motorcycle driver that he knows or can show me that he's there. You can see obstacles in front of not only the next car, but a couple of cars, and you can see around corners. So I can see basically that there is an ambulance driving into a crossroads around the building long before I hear or see that car. And even the traffic lights can react. The one important thing is that market does not come to existence without data security. So the same chip we are applying to 3/4 of all passports, biometric passports worldwide, we are also using exactly the same silicon with a different temperature range. We are also using for these systems, because these systems need to say, like I say at the United Airlines gate, hey, I'm Lars, I'm allowed to fly here. These systems say, hey, I'm an ambulance, please switch the traffic light to green for me. If we would not have this authentication and data security, I can tell you one thing. My car would tell every traffic light, I'm an ambulance, please switch me to green. Because then I'm 10 minutes faster in the office than any one of you. So this would be smart traffic management, a bit selfish on my side, but of course we cannot afford doing that. The next thing here on that slide is basically what we call truck platooning. So you can create virtual tow bars. So one truck is driving, and the others are following at a very short distance on a virtual tow bar, so to say, saving fuel, and the other drivers that are following truck number one, they don't have to drive themselves. And you can see this here now in the next video, so if we could start that little video, then... Yeah, so the truck basically could even negotiate the front truck with the traffic lights and get the traffic lights to a green light extension. And the good news is, out of all these techie dreams here, this is reality already. So we have this truck negotiates with traffic light use cases already in Hamburg, in Germany, running. And these trucks here from DAF, but also trucks from Scania and other suppliers, they are driving in the Netherlands at 50 to 55 miles an hour of speed at a distance of 11 meters behind each other, and they use the radar systems that I just mentioned, and they use the V2X, so the car-to-car communication systems. And that works exceptionally well. So the message latency is less than 5 milliseconds, so really from I put my foot on the brake in the first truck, and truck number 5 knows that and starts braking as well. And you can imagine if you have all these delay seconds of a human driver in between there, that would be totally undoable. But here we are going really into autonomous driving of the extreme. Yeah? Very interesting. We are big-time business developing here in the US. Here you see Rick Lemmer, our CEO, and Kurt Sievers, my boss, who's heading the automotive division, together with Anthony Fox. And then, of course, we are driving with the smart cities, amongst others, Austin, the legislation for these V2X systems, but also in Asia and Europe. There is a lot of field trials going on in that domain. And what you see there is the silicon needed for that is, again, such a tiny module of 3 by 3.5 centimeters. So it's really an interesting offering. You can place it into shark fin antennas under the roof, pretty easy, pretty simple to be implemented. And you will see this end of the road here in the US, first going into market with GM cars. So really, really interesting to see this. So the next part, very quickly, is the sensor fusion domain. So what can we offer in that area? Basically, how do we make sure that all that sensor data comes into one thinking machine, into one big brain, and how do we calculate the driving advice out of that? Well, NXP, we have taken from our digital networking division big processors that are used normally in server farms. So in cloud computing, 8-core ARM machines, 70,000 DMIPS. You see it here to the right, to the left of that slide. And then also we have combined this with vehicle safety processors, vision fusion processors, and we have a combination of those two. We have put this into developer systems, 19-inch racks, so universities, tier ones, car OEMs can and are playing with that at the moment. And you see, the box was blue, therefore we called it blue box, so nothing more sophisticated in there. But basically what we are using is the following. This is industry-ready components. These big fusion processors are, for example, used in autonomous flying already. So a lot of the flight computers that are operating planes over our heads are based on that silicon. We have all of that ready qualified, and in principle, everyone who wants to have a ADAS system in his car can design with these components and an industry-ready system. The system is open, so you can put your programming languages on, and the approach of NXP is, of course, to providing the hardware and to invite everyone bring your algorithms, bring your software on top of these systems, which is, of course, very inviting for the big tier ones, Conti, Bosch, guys like them, or the big car OEMs, because they have quite a deep know-how already on these self-driving systems. And what is very cool is the power consumption for such a system is in the range of 40 watts. There are others out in the market who are going in with water-cooled 250 to 300 watt systems into the market. And what we hear at the moment out of the market is that this approach here is a very interesting one, because of course you don't need the big water cooling, but you can afford 2 or 3 of these redundant systems, and you are not even at half of the power consumption of these big machines. So with all of that, quite an interesting play at the moment, and let's see how that evolves over time here. So the press is very eager to look into that. So, but what would all of these components be without a good neural network, so a neuron system inside the car? What I mean is the in-vehicle network. So since the mid-90s, you know, all these Ken-Lin FlexRay systems that we have, and NXP was and is market leader for these physical layers to the wiring harness, basically to all these interfaces to the wiring harness. And a few years back, then first of all, BMW came to us and said, can you please license a standard from Broadcom? Broadcom had developed an Ethernet 100 megabit standard. So in PCs, you have the normal 100 megabit lines, but on 4 wires. Broadcom did this on 2 wires, and we licensed that standard from Broadcom, developed our own ICs, Automotive Robust, out of that. We call it, they called it Broader Reach, and we adapted that into the automotive domain. And what you see there is Automotive Robust systems. Now you see down there the automotive grade Ethernet connector and the automotive unshielded twisted pair cables. So this is how Ethernet looks in cars. But that, of course, helps us shuffling these huge amounts of data from the sensor systems into the vehicles. Ethernet has another flavor, the so-called deterministic Ethernet, which is very, very much needed for all these X-by-wire technologies, so fly-by-wire, drive-by-wire, break-by-wire. Because what you have is you can give timestamps and can attach timestamps to the data packages. So what needs to travel at priority and what can afford, let's say, delay times. Because the last thing that you want to have in your car is that the system says, hey, sorry, Lars, I'm just dealing here with the infotainment content. I'm braking only in 1 or 1.5 seconds. Yeah? That is, of course, not what you want to see. Yeah? So this deterministic Ethernet makes a lot of sense there to having over the same network critical and non-critical data routed. One car generation ago, premium cars had in the range of 100 to 140 control units. So even the heavy electronic cars, yeah? So the BMW 7 Series and Mercedes S-Class and these type of vehicles. In one generation from now, these cars have in the range of 250 control units, 250. And they all need to somehow be networked. So in other words, also the network architecture in the cars is going to change dramatically. You have these security requirements, but also basically the IT guys who are responsible for the car network, they are looking at that and say, okay, it's like a big IT building with 250 departments, and we need to somehow get this linked together. And this is why you see suddenly these networks looking not anymore like one CAN wire and all the ECUs are plugged into it, but what you see is you have domain-based architectures. So you see basically a powertrain branch, you see a head unit branch, a driver assistance branch, and they are all separated and operated via central gateways. And this is, you see here the various compartments. This is where then the Ethernet switches and physical layers come in, and there is a lot of architecture going on. So these networks are big time changing, which is good for us because I can now copy from my sister divisions a lot of innovation and electronics, also for the last chapter of my pitch here, and this is security. So basically, what I said prior is NXP has quite some history in data security, in banking security, e-health, e-government. We are also the market leader for all sorts of car access systems, so passive keyless entry systems, long-range car keys over 1 kilometer of distance, you can operate your car and all of that stuff. So this is all available as know-how, as IP in the company. But now, how do we deal with securing such a big IT building with 250 departments? Well, the answer is very simple. Look at it like if you would look at your house. You have door locks, crypto controllers, and of course now you have to look at the entire system again and then put the right lock to the right door. In other words, you're putting, of course, very heavy locks at the interfaces to the outside world, at your front door and at your back door. So in the case of my family, maybe also a heavy lock at the wine cellar, but that depends on, of course, which assets you want to protect. So in other words, these heavy locks don't make sense everywhere. So in your house, for example, between kitchen and living room, if you have a door at all, you definitely don't have a heavy lock that you want to open and close each time you walk between the rooms, because then it starts getting pretty inconvenient. But of course, what we are doing is, in the entrance hall of your big house with the 250 rooms, your central gateway, you're having a few watchdogs sitting, so a bunch of nice Dobermen. And if you want to walk from the infotainment wing of your building into the engine compartment wing of your building, then make sure these Dobermen like you, and you don't get them attacking you because you're doing illegal stuff. So for a burglar, that would be a challenge. The other thing is, of course, so this is the secure gateways. The other thing, of course, is we have in each of the rooms, or at each of the doors of each room, we have a lock, which is less heavy security, but it is at least a lock. Number 3, this is the secure microcontrollers that came into our portfolio from the Freescale side. And then number 4, in terms of data security, that we are developing at the moment is not really security in the literal sense, but I would call it consistency checking. So just assume that a trailer hook control unit shouts over the CAN bus, "Hey guys, lower the windows." Then at least someone should ask, "Hey trailer hook, how come that you sent this command?" Yeah? It's like I have guests at home and they suddenly show up in my wine cellar or in my bedroom, and I don't expect that. I have not invited anyone there. Then at least I should become suspicious. So it is basically network hygienics that we are also applying. In techie words, I would say authentication. Yeah? So in other words, these are the 4 examples of data security that you see. And with the door locks that NXP provides, with the solutions that we provide, we can secure the entire car. And we can say absolutely clearly, all the hacking cases that you have seen in the last 2 years in the press would have been impossible with the right application of the silicon that is already in place. And that's, of course, good news on the one side. It's a great market, of course, for us on the other side. But it's an absolute must-have for trusting self-driving cars. Because the last thing that you want to have is that your car surprises you in the morning when you're driving to work with a 90-degree right turn into the ditch. Yeah. So in other words, this is the overall security portfolio. We are calling it a 4-component concept. We are adding number 5 for the car keys. And this is what we are driving at the moment into the market. And here you see just a few of those storytelling pitches, engagements that we are driving. So you see to the top left, you see this truck negotiates with traffic light use cases. Then next to that, I'm sitting there with Andy Greenberg at Frankfurt Motor Show, and we are discussing our security solutions. Andy is the one who hacked the Jeep. Then what you see there, this Storm bike, as it is called. Storm is the name of a motorcycle where Dutch students have built a 400-kilo electric motorcycle, and they are driving around the world with that thing, and NXP has heavily sponsored that. And what I have here at my finger is a nice ring, and I did not get this from my wife, I got it from my boss. So, bit funny, but what is in here is near-field communication, NFC, and one of our crypto chips. So I can touch the bike handle, and it is a poor man's immobilizer. I can go waterproof with that thing onto a jet ski in the water. I can drive. I can touch my door handle. I can even touch my mobile phone. I don't need to enter a PIN anymore. So I have very different variable form factors suddenly of crypto electronics, IoT electronics, electronic dust, as we call it. And this even is ending up in long-range RFIDs, 20 meters of distance in license plates, where my car uses its license plate in Hamburg, not anymore as just showing optically that this is the car that is registered for Lars. No, my license plate is used like a contactless badge. So my car is driving to the gate, and at a distance of 20 meters, the reader sees there is Lars's car coming. So the gate opens up automatically. And I've glued even this electronics into the school bag of my little daughter. So just imagine the case, the traffic light sees, school bus opens its gates, 40 little devils run out, and the traffic light sees, oh my gosh, there is 40 vulnerable road users approaching me. Traffic light goes immediately to green, stops these road trains here, and informs me via car-to-car communication, hey mate, slow down. There is vulnerable road users directly in front of you, and by the way, I'm anyhow switching to red. Yeah? So no need to go head over heels. Furthest out here on the top right, we're even talking to drone makers, because car-to-car communication is the same like drone-to-drone communication. And an anti-collision transponder of United Airlines and Lufthansa has a weight of 10 kilos. If you want to deliver a 3-kilo Amazon parcel and you have to lift up first an anti-collision transponder of 10 kilos, this is prohibitive. But the 14 grams module works. Yeah, so we are also playing in that domain, and you will see that coming pretty soon, I hope. Concluding on that entire pitch, we are going really in a disruptive way in the automotive industry, and disruptive way also for the silicon design into self-driving robots. We are accelerating there by selling ready-made systems, as I had just pitched them, so for car-to-car communication, radar, fusion, and security, and a couple of others as well. And basically, what you see there is, it is not that much driven by Moore's law, what we have in our hands, but now, by going one level higher, trying to understand the overall system, and trying with what we have in terms of physical circuit capabilities in our hands, trying to drive this really into disruption for CMOS one-chip radar systems, for one-chip car-to-car systems, for tiny, highly energy-efficient sensor fusion, robust and high data rate networking, and of course, last but not least, with all hacking proofness and security. And with that, I hope I was a good CEO for you this morning, so Chief Entertainment Officer, and could show you a bit of the passion and what we are doing. And of course, I'm around the entire day for questions and looking forward to discussions with you. Thanks a lot.
Thanks. Oh, well, I just, on behalf of the DAC Executive Committee, well, why don't you stay over here? All right. I just want to present you with this this flag, and really thank you for a terrific
keynote. Thanks a lot. So we have to do this photo
thing?
Yeah,
there we go, there we go. Do the photo thing. All right. All right. And yeah, we're out of time for questions, but if you have any questions, Lars said he'll be around. You can come on up, and we'll see you out there for coffee. Thank you.